Hi everyone, this is the last video for sorting, also the last cock video for it. I haven't yet made video number 2 though, so don't be surprised when you see these out of order in box. The last thing I want to do in cock is have us write functions that can identify sortedness. Okay, so we've built a bunch of intuition in the last video about what makes something a good sort function, um, and now I just want to be really concrete. Here's what it means for something to be a sorting function. First, it takes a list and returns another list of the same kind of thing, sorted ascending, right? So it should actually be whatever output you get should be sorted. Where ascending here means it never goes down. You can have duplicates and they'll be the same value as you go along, but it should never go back down. Second, the output list should be a permutation of the input list, right? The list we get out should just in some sense be a rearrangement of the original list. There should be nothing new and nothing should be removed. No additions or deletions. So let's write some functions that can identify precisely these conditions. All right, the first function I want you to write is a function is sorted. It should take a list of naturals, and it should return true when the list is sorted ascending. Now, there's no reference to an original list. This has nothing to do with the permutation requirement. We're going to deal with these two requirements separately. Okay, so is sorted. You take a list in L, and then we'll walk down the list and make sure that it never goes down. Okay, how are you going to do that? The the Once you sort of think through how you want to do that, you'll then have to say, okay, well, how do I encode this in cock so that cock accepts my function, that it'll terminate? And we have two tips here that I think are relevant. The first is you can use a nested match to sort of figure out what it is you want to do recursion on. Right? So long as the thing you make a recursive call on is something you found by matching on the principal argument, the decreasing argument. Here, there's only one argument, so you'll be fine there. So long as that's what you matched on, cock will decide your function is terminating. Right? That'll be fine. If every recursive call is on something that is the output of a match, something you bound in a match as a substructure. And then there's this like extra syntax, which if you want to use, you can use. It turns out that like this will be useful. So like if I was matching the concrete list 1, 2, 3, 4, 5, and I wrote this pattern, what this is doing is it's saying, okay, well, there's my list in this case has H1, the first thing in the list, and then H2, the second thing in the list. So there's like at least two things in the list, and then some tail. But I want to give a name to this whole list. So I put it in parens and I write that as. And over here, you can write some expression. Here I've written, this is not code. This is me just saying, hey, these will be what things will get bound to. So in here, if we write some expression here, H1 will be 1, the first thing in the list. H2 will be 2. T2 will be the list 3, 4, 5, and T1 will be the list 2, 3, 4, 5. And cock will allow you to do recursion on either of these. Might be useful. I'm just saying, it might come in handy. Okay. That function covers this bit that characterizes sorting. What about the permutation bit? Okay, so we need another function, is permutation of. So here, what we have is we frame up for you what the function is. We'd like you to implement the function, and then we want you to define a list of test cases, right? It'll be a list of pairs of lists of nats. Here we want 5 test cases, so it should be 5 pairs of lists, so a total of 10 lists in this entry, where the first one is a permutation of the second. And then here there should be a list of 5 pairs of lists, where the first one is not a permutation of the second. Now, a thing you could write here would be once you found one list that was a permutation of another, say the empty list is a permutation of itself, you could write 5 copies of the pair empty list, and you would be fulfilling the letter of the law but not the spirit of the law. We want 5 distinct, right? 5 different notions of permutation. Ideally, your tests are good ones in that if someone had a bad version of this function, it would catch that. So you want to exercise different bits. You talk about empty lists with one duplicate, with more duplicates, things like that. That's what we want you to be thinking about. Okay, how does this function work? Right, so we give you some hints about like, how does this work? I see really 2 ways to go here. One way to go is to say, look, you have 2 lists, L1 and L2, right? Your function is going to have this type. And you're just going to walk through one. Let's just say we walk through the first one kind of arbitrarily. So you get an x from L1. Try to remove exactly one from L2. If you can't, if no x occurs at all in L2, there's no way it's a permutation. You had an x in L1, but it's missing in L2. Forget about it. Okay, if you find one, remove that one from L2, leaving any others, but you don't want to change, you only want to decrement the number of x's by one. So drop one from L2 and then keep going. Eventually you should end up with an empty list and an empty list. That's one approach to solving this function. Here's another one that I think is maybe a little bit more work. You could write a function that just generates every permutation of L1 or L2. It doesn't matter which way you go here. And then you write a function that tests list equality on lists of naturals. Right? You've already seen how to test list equality on strands of DNA, and the idea will be similar. And then just see, like, look, generate the list of all permutations and see if L2 is in it. Right? So or generate the list of permutations of L2 and see if L1 is in it. Either way, it doesn't matter. Both of these work great. Both are going to need you to sort of invent and define your own helper functions. I think this version's a little bit easier to write, but that's just my bias. It also happens to be the more efficient one, so it seems like this is a thing that people sometimes care about. We're not caring about efficiency here. The tests we're going to run your program, it really doesn't matter. But if you care about that, then this is the more efficient one. This one is maybe an interesting one because you get to write that function that generates all permutations. It's a fun one to write. We'll be thinking about these things later on when we do some proving of our sorts correct and talk about combinatorial. Okay, in any case, what do we want from you on this? We'd like you to finish this definition. You'll have to write some helper functions. You have to come up with what they are, too, based on the approach you want to take. And then you have to write 5 unit tests here and 5 unit tests here. And then you'll know that, okay, at least your function and your unit tests hang together when this passes. If you like, you could change this to a for all b just for fun. Now, when this passes, that doesn't mean that you're done. That doesn't mean you got it right. Right? Your test could be wrong. Your test could miss something important here. So it's important that you think pretty hard about this. Okay, that's it. I'm going to do one more super quick video just walking through how to run the insertion sort algorithm. And then that'll be that. That'll be all of day 6. Okay, good luck, everybody.